Tell us about Stralis.
Thanks, Chuck. From the waters now to the skies. Steffen Geries, CEO of Stralis Aircraft. So we built a mission-free aircraft based here in Brisbane. It's a pleasure to be here at that event, also meeting some familiar faces in the clean tech space, and particularly also in the hydrogen space. So this is where we sit. Let's start with the problem. We already heard yesterday, also today in some of the panels, that aviation is one of these hard to abate sectors. And let's talk a little bit what that means and why that is. So looking at the energy that is required to fly a plane, to get it into the air, to sustain a flight and make some distance, it's tremendous amounts, right? And fossil fuels, they have that big beauty of being very, very energy dense. To put that with some numbers and perspective, take an Airbus A320 single-aisle narrow-body plane. I leave the 737 a bit in peace. It's got some issues at the moment. But similar category aircraft, it weighs about 40 tons when it's empty, and you fuel that up with about half of that weight with fuel, so 20 tons of fuel for a normal operation. So about half of that empty weight goes on top in fuel, and you sustain a flight with that. So if we take batteries, for instance, like even the most sophisticated chemistries and technologies that are available at the moment, they have about a tenth of that energy density of Jet A fuel. So you need 10 times that weight, so 200 tons of batteries. If you leave efficiencies out of the game, electric propulsion system is way more efficient than a fuel-burning engine, say 3 times, so you bring that down again, but still will be about 70, 80 tons, so that's not gonna fly, literally. We heard a lot about SAF, and SAF is a critical element, sustainable aviation fuels. So essentially, biologically synthesized fuels that are burned in a conventional, slightly modified fuel-burning power plant engine. So given the size of the aviation sector and given the need of flight, so most of us would have flown, are flying regularly, even if it's only a small percentage of the global population, 10% I think we heard recently, it's still for our developed economies, particularly in Australia, it's just crucial. We need to be able to fly also long distances. And the only foreseeable pathway to decarbonize or make that net zero in emissions is sustainable aviation fuels. That plays a huge role, particularly in a long distance flight. But if we go to shorter distances, small to medium ranges, say 3,000 kilometers, this is where other technologies will play a role. Battery electric, as we just heard, is very difficult. It really only has a future in the very small ranges. The core of our team actually comes from battery electric flight, myself as well. We worked at magniX before. We developed electric propulsion systems. We flew them on some world firsts, the eCaravan and the eBeaver in the States in 2019, 2020. And we learned electric propulsion, electric flight is possible, but not with battery if you want to have a viable business case. It needs to be a different fuel source. And this is, for us, we came to the conclusion this is hydrogen. And the market we are targeting is these planes you are seeing here, a Dash 8 or an ATR 42, 50-seat category aircraft. Why is that? Well, these are turboprops that are very expensive today to operate, even with fossil fuels, 65% more expensive to operate than a single-aisle narrow-body aircraft like the 737 or the A320. And that has kept that market dormant, and there is a huge potential sitting there. If we leverage that technology, hydrogen electric, to be more particular. So we use hydrogen, bring it through a fuel cell to create electricity to drive an electric engine that drives a propulsor. May it be a propeller, may it be a ducted fan, may it be a rim-driven fan, whatever the best technology for the application. For these kind of planes you're seeing here, it's most likely a propeller because they're very, very efficient. With that, we lower the operating cost by 50%. And that is mainly driven by the reduction of maintenance cost. There's barely any maintenance in these system components I just described. And the other big element is the cost of fuel, so hydrogen. Hydrogen production, obviously our business model rests on. The hydrogen industry is coming up, the cost of hydrogen is coming down, hydrogen is produced at a large scale, and this is what we're seeing is happening. So we now have to meet the right time to bring that existing technology onto an aircraft certified, which is also a lengthy process. 50-seat aircraft is a smaller aircraft, so picture you replace a 737, A320 type aircraft with 3 smaller ones, still more efficient and more cost beneficial to operate, and replace these aircraft and also open up new direct routes. Not everyone wants to go through the main hubs when flying regional, for instance. You can have more direct flights, and the market potential that's here is quite significant, and that's not us making up the numbers. So Airbus, ATR, Embraer, their market potential analysis shows a market for these aircraft in the next 20 years of roughly 140,000 aircraft. Again, to put that into perspective, if you think automotive, 140,000, that's not a lot, right? If you think aerospace, like the overall fleet globally in operation at the moment for single-aisle narrow bodies is around 25,000 aircraft. So 140,000 is a huge number in 20 years. And that also goes into manufacturing. You need to think aircraft will need to be manufactured in a different way. We can't do it in that highly manual way as it is happening at the moment. With that in mind, we have a very bold goal, the last line there. We want to get a sizable chunk out of that market potential, 50,000 aircraft by 2050 in that 50-seat category. One step back. How we go there from a product development roadmap. Our launch product will be a retrofit. That's the top one of these two you can see here. It's a Beech 1900. It's a pretty renowned in that segment aircraft, distributed over the globe, successful in operation, has various advantages for us to convert it to hydrogen electric. It is usually a 19-seat aircraft. So one specialty about hydrogen is it's difficult to store it in the wing, right? That's maybe one of the downsides. I spoke about battery having a tenth of the energy density than Jet A fuel. Hydrogen has double the specific energy density, but in terms of volume, it's the smallest element, right? To package it, it's very difficult. Needs 7 times the volume than Jet A fuel. So liquid fuel is beautiful. It goes everywhere in the wing. You can store it very easily. Hydrogen needs a more bulky cylindric storage device if you do it gaseous. One trick here as well is we bring it down to minus 253 degrees Celsius and liquefy it. And this is another piece of the technology that we are working on, or using liquid hydrogen. So this way, and also the high efficiency of the propulsion system, we only need about double the space. But you can't store it in a wing. It has to go into the fuselage. And then you reduce passenger count, and that increases cost per available seat kilometer. But with the lower cost in maintenance and fuel cost, we still undercut the operational cost of a conventional aircraft. Also, if you take the requirement of the wing to store fuel, you can do lots of amazing things with the design of the wing, with the aerodynamics, producing more efficient aerodynamic structures, and also having manufacturability in mind, simplifying that whole process. And this is where the SA1 comes in. That's the 50-seat new design aircraft entering service in 2030, which is a clean sheet aircraft. And thinking manufacturing, which is the topic of that conference, here we have a large potential to actually design that for advanced manufacturing, addressing that high volume market. So from the get-go, from the concept design through preliminary design, we already want to consider advanced manufacturing technologies to achieve these high numbers in aircraft manufacturing and bring sustainability into that thinking as well. So it will be a design which allows highly automated manufacturing, has obviously comfort of the passengers in mind, stores the fuel also in the fuselage at the rear, has the engines at the rear, which makes the cabin way quieter, and also will have an automated fly-by-wire system. Looking into the future, crew reduction, single pilot operation, maybe even further down the line, way beyond what's acceptable today, but automated flight, autonomous flight, for instance. 3,000 kilometers of range, 600 kilometers an hour cruise speed. So that's fairly conventional figures in aviation at high scale, huge business potential. So we are actually real. We are currently in operation, 12 people strong, founded 2.5 years ago here in Brisbane at the airport. We are working on a technology demonstrator at the moment that you can see here on that picture. We have 2 of those aircraft. That's a Beechcraft Bonanza, which is, I always compare it a bit where the Cessna is the VW Golf. This is a bit the Porsche 911. It's like a sporty general aviation aircraft, which we have selected. The one is flying, which we call Bonnie, and this one here is the non-flying one, which we call Clyde. Clyde does a good job at the moment in testing out our technology, so we have spun the prop first in September last year. This is where this photo, some late evening, was created, and we have done some high power testing in December. This is still running off power of the grid, but we are bringing hydrogen in the mix as we speak, and will target first flight by the end of this year. Thank you.